right, so it's time to proceed to the next talk. That's a talk by a PhD student from LAAS-CNRS. His name is, what is your name? Thomas Hoger, sorry for that. The presentation is titled Multi-Domain Anomaly Detection in 5G Networks Through Continuous Dynamic Graphs. It sounds like Philippe Owezarski's work, right? Where is he? Is it true? Yeah, good. The floor is yours.
Okay. So, hello everyone. My name is Thomas Hoger. On m'entend bien? Où ça? Ici? Okay. Hello everyone. My name is Thomas Hoger. I'm a third-year PhD student at LAAS-CNRS. And today I will present you the work I did with Philippe Owezarski, which is my supervisor, and Mariamdouni, which was an internship at the time we worked together. Our work is part of the POPR Network of the Future initiative, and more specifically to the ISEC project. Today, my talk will be about 5G networks, machine learning, and attack detection. I will begin by introducing the 5G context in general, then showing example of 5G attacks. We then will see the literature of detection system in 5G. We will propose a new formalization, which is graph, and we will introduce machine learning models on graph. Then we will see the experimentation and the results. First, I will try to explain the basics on how 5G work, so starting from the very beginning to the people that are not familiar with. I won't go too much into detail because it's more of a motivation in our case than the real contribution, and it is not required to fully understand 5G to understand the detection system. So to start from the beginning, obviously, we have a user equipment, which is a phone, for example, or a laptop, or any piece of IoT that want to connect to the network. It is called a UE in the 5G, so you will see the acronym a lot. To connect to the network, it will have to go through an antenna, obviously. It's called the G-node-B in 5G, and it's communicating with a radio signal. The antenna doesn't simply connect to the internet directly. Instead, it communicates first to something called the core network, which verifies access right and performs multiple other tasks. The core network consists of multiple independent entities called network functions. They communicate with each other and with the G-node-B via IP connection. Each of these network functions have its own specific role to play. For example, there is the UDM, which serves as a database for user information. The AUSF handles authentication and manages cryptographic stuff. The UPF acts as a router for user traffic, and in 5G in general, operators can create their own network function depending on their need. So there is an infinite type of possible network function. There are various types of communication channels, some of which are specific to 5G and mobile networks. For example, the phone and the G-node-B use a protocol stack that include NGAP and NAS protocol to communicate with the core. User traffic is encapsulated in GTPU, which is then passed through the UPF. And the user session management is handled by a protocol called PFCP. Finally, most network functions communicate with each other via API calls, so basically just HTTP. So, well, that now we have a rough idea on 5G, how 5G works. We will see what the changes are from 4G and how does it impact the anomaly detection. Of course, there are plenty of changes, some of which are, for example, on the physical layer. But here we will focus on the major changes related to the network communication. First, one of the changes is the virtualization of network function. We are moving away from a monolithic system where the network function run on dedicated hardware. Instead, with 5G, thanks to virtualization, we can have network function run on Docker container or virtual machines that can now be run on any type of hardware, just like microservices. Next, we have software-defined network. Before, the system was static, and we couldn't change the system once deployed. Now, since we are using virtualized machines, they can be easily started and stopped, so we can dynamically change the network architecture. This dynamic deployment is also made possible by the shift to a service-based architecture, which is the use of API calls to communicate between functions, which provide a standardized mean of communication between network functions. Because of these changes, 5G network is increasingly resemble distributed systems in their design. Well, we've seen that 5G brings a lot of cool features, including greater dynamism and flexibility. But as you may know, security benefits come at the cost of an increasing attacking surface. So let's look at a few examples of attacks that are possible because of the change brought about by 5G. Well, the first type of vulnerability that arises is about virtualization. When you add a virtualization layer, you also expose yourself to the possibility that an attacker can escape that same layer. potentially gaining access to other network functions hosted on the same machine, also obtaining secrets or doing lateral movements to connected machines. Second type of attacks you must be familiar with is the man in the middle. Because function can now be dynamically added and removed, there is a risk that an attacker could register malicious network function that could position itself between two legitimate ones. Next, since the API calls are now standardized, it's also much easier to attacker to do fuzzing and find vulnerabilities in the parser. 5G also introduced a mechanism called slicing. It allows to define some kind of subnetworks, which each providing different level of quality of services. Those subnetworks are supposed to be isolated logically. However, some network functions are sometimes shared between slices. And we found some attacks that allow an attacker to pivot from one slice to another where he normally doesn't have access. 5G networks rely much more on software to operate than previous network. Those software relies heavily on third-party code, library, and most of which are open source. We can then imagine that there will be many more opportunities for an attacker to plant a backdoor in the supply chain. As always, features and flexibility come at the cost of an increased attacking surface. Yet, because of the heterogeneity of this surface, it's not possible to secure them all at once. So we decided to focus on the network traffic and consider the other surfaces as intrusion vector that can allow an attacker to compromise a GNOD B or a network function, for example. Network traffic consists of user traffic, like video streaming, obviously, and control traffic, which is triggered, for example, by UE registration or deployment of new network functions. That's the stuff that goes behind the hood and that the user doesn't know about. User traffic doesn't really interest us because it involves a large volume of packets that are encrypted from the operator perspective. On the other hand, control messages are much less frequent and have a lot of value. They are encrypted, yes, but the operator owns the machines and the secret, so we can decrypt the traffic. We focus on the control plane and more specifically to the upper layer protocol, which are, from our point of view, the most characteristic of the 5G shift to distributed systems. Now that we know our scope, we will try to characterize the attack we consider. There are three different types of dimensions we identified in the 5G network literature, and we can use them to categorize any kind of attacks. This classification is not groundbreaking and is rather intuitive, yet even if the three dimensions must be considered together, we will see that it is rarely done in the state-of-the-art of the detection system. The first anomaly dimension is the semantic one. Those are the packets which content is intrinsically problematic. It could be an endpoint, for example, displayed here with the endpoint dummy, which is not existent in 5G, or any kind of field in a packet, not especially an endpoint. This type of anomaly is rather easy to detect, and we don't require any context. The second type of anomaly is the sequential ones, which is characterized by the succession of semantically similar packets. This packet can be legitimate when examined individually, but it's the sequence they constitute that is problematic. To detect them, you have to pay attention to the temporal context in addition to the semantic one. Finally, the last type of anomaly is the topological ones. The best known example is the man in the middle, where a same exact message is redirected to another entity. The forwarded message content can be legitimate, and the only anomaly is about the redirection, not the content. Here as well, you will have to pay attention to the context of the interaction to notice the anomaly. Okay, so now we will take a look on what is done in the literature, and we will check if the proposed solution considers every or only some of the dimensions we explain. First, we have ADSEC 5GCN, which proposed to formalize exchanges as a sequence of interaction between entities and to look for anomalies in the sequence. They use recurrent neural network, so it's supposed to work well with temporal anomaly detection, but because they don't take into account the content of the packet, they can't detect semantic anomalies. This format also allows to take into account, to some extent, the topological context, but only for short-term interaction, and it will struggle when they are distant in time. 5G Sigward is really similar, and the most important difference from the previous paper is that they add the information of the API endpoint to the sequence. So it's a bit better because you have a bit more semantic information, but it's still too poor, and it can't handle protocols other than HTTP. Prov 5G is different. This time they use provenance graph formalization to represent the network interaction. So we have nodes that describe entities such as network function and UEs. And for each message involving two entities, they make an edge containing the packet payload. The graph formalization is well suited for topological analysis, yet in their case they lack the temporal dimension, and the fact they group the information into a single node significantly limit how the information can be used. In their case, they design a specific detection algorithm for each attack, which is kind of equivalent of a switch case. It's way too simplistic and heavy. Finally, we have GSAD, which also formalize their data as a graph. This time they have on the edge, they represent the packet as a stream of bytes on which they try to extract some semantic meaning. To do this, they'll consider the bytes as an image and use convolutional neural network on it, which is supposed to learn pattern on the stream. It works well on actual images, and we've seen good example of result outside computer vision and image, so it could work, but in the case of 5G, representing the stream creates a lot of issues, and this is not designed at all to detect small value shift in the identifier. For example, if you look at the IP address, a small value shift have a lot of impact, and doing convolution on image can't detect this shift. In addition to image convolution, they also use recurrent neural network and graph neural network that respectively handle sequence topology. They are therefore the only paper we found so far to consider the three domains at once. Now we will see what formalism we chose and how do we represent our attacks with it. The difference between our formalization and those of Pro5G and GSAD is that we represent a packet as a subgraph instead of a single edge between entities. We model each parameter as an individual feature node connected to the central node, which represents the packet. The feature node are the purple one you can see, and the packet node is the blue. The feature node contains the feature value, and the edge connecting it to the packet contains the name of the parameter. Each time we encounter a packet, we create a new subgraph. For every parameter, we add a new node if it have not been seen before. If it have been seen before, we reuse the existing node, which allows us to connect different subgraphs together. By splitting the feature this way, we can create links between attributes of different packets, enabling us to capture interaction based on shared parameter rather than only looking at the source IP address and the destination IP address. This representation go down to a very low level of detail, allowing us to identify exactly which parameter is suspicious. As a result, the approach is highly explainable. Now we will go back to the anomaly example, and we will see what they look like when converted to a graph. Here, even if packet 3 resembles the previous two, it is an anomaly because it's connected to an unusual node. The MI doesn't exist in 5G. For the topology, we can clearly see on the graph version of the man in the middle that the second packet is a redirection of the first message to another destination. Finally, for the sequential anomalies, the graph may appear normal, so we need a way to incorporate the temporal information. We will see shortly how we integrate it to the graph. We therefore obtain a formalism that is well suited for semantic representation and topological analysis, and we briefly mentioned that graph neural networks are well suited for this. We will now introduce the basics on how GNN works and how to incorporate the sequential aspect we are missing. In essence, graph neural networks are very similar to convolutional neural networks. The difference is that instead of working on images, they work directly on graph. Both methods make an average on a location, group of pixels for an image, and node neighborhood for a graph. The idea is that each time you repeat the process, the convolution, you get the information of an incremented distance. On the GIF, for example, after 2 convolutions, you see that the central node will contain the information of its neighborhood up to distance 2. Okay, now just a bit of history about GNNs. The first time the term was mentioned in a paper was 18 years ago. And we had to wait 9 years later for a paper called MPNN to formalize this type of model. So the topic is very recent. Most of the work in the field operate on one big monolithic graph that doesn't evolve in time. It's okay for them because some paper like do chemistry and analyze the atomic composition of molecule, and in their case they don't need the temporal aspect. But in our case, we want dynamic graph, which is an even more recent field, with the earliest paper published only 5 years ago. Dynamic graphs are split into 2 kinds. The first one is the discrete time dynamic graph. These are the easiest to understand and implement because they are simply a sequence of graph snapshots. This approach allows to use the standard GNN model combined more or less directly with a RNN to capture temporal dependencies, which is the approach followed by GSAD, the last paper I presented. The main issue here is that they are really heavy and bad at detecting long-term dependencies. So the second type of model, the one we used, is the continuous time dynamic graph. Here, instead of representing the data as a static graph or a sequence of graph snapshots, we model it as a sequence of graph events. For each edge, edge that we would add in a traditional graph, we create an event defined by the edge and the two nodes it connects. This changes the algorithm used by the GNN, but it enables a fine-grained representation where no information is lost. We will again show an example of the transformation, first to a graph, then to a continuous graph. At this point, you should be familiar with the first part. Each packet creates its own subgraph. With the continuous time perspective, each packet previously connected to 3 nodes can now be represented as a sequence of 3 events ordered over time. So you have as much event as you have a number of edge. The most important part of our contribution is the formalization of graph, which bring together both the 5G domain and the very recent field of continuous time dynamic graph. Our formalization provides both explainability and the ability to handle the 3 dimensions at once. We will now look at how to put this into practice using state-of-the-art continuous GNNs, because designing new GNN architecture is a research field in itself, so instead of trying to do our own, which I'm not qualified to, we will focus on comparing the performance of the best existing model from the literature. This also allows us to validate our intuition that the continuous time graph perform better and to analyze which parameter influence our results the most. We will present one of the most popular examples, TGN, published in 2020. Most dynamic GNN follow a very similar architecture overall, so the TGN example is representative to the general concept of this family of model. Sorry, I went the wrong way. So the first step is to create a message, which is the name of a vector containing the encoded information of our event. For the node vector, we are initially setting them to null. For the edge, we want to encode the name of the parameter. In 5G, there is hundreds or thousands of features that we could want to consider. We could encode them each as an orthogonal vector, but its dimension will be equal to the number of features, which would be way too big. In addition, the vector orthogonality will slow down the learning, and we will prefer the encoding of 2 semantically similar nodes to be close in the latent space. For example, IP address for the destination and the source should be near in the latent space. So because those features are text, we could consider using natural language processing for the feature embedding. But it's still ongoing work on our side, and we chose to select the 40 features we believe to be the most important for the detection of the attack we identified in the literature. Then, because the size is much more manageable, we apply one-hot encoding and obtain a vector representing the edge feature. I mentioned that the node vectors are initially set to null. However, if a node has already been seen, we replace its vector with the saved version from the memory. Then we consider all the neighborhood from the source node we are currently processing. In the context of a continuous time graph, the neighbor corresponds to every event in which the node appears. Then we perform an aggregation step, meaning that we combine the multiple messages into a single vector, for example, by taking the average. This results in a vector representing the one-hop neighborhood of the central node, which is, in our case, the packet itself. Now we pass it, the aggregated vector and the memory, through a recurrent neural network to manage the sequential dimension and create a new embedding that will replace the previous value. To perform the convolution, we retrieve the node's neighborhood up to n hop and pass it through an encoder. Here it's a multi-head attention mechanism, which outputs a vector representing the extended neighborhood. We then pass the vector through a multi-layer perceptron to obtain a probability of existence of the edge. We then compute the loss by comparing the predicted probability to the ground truth. For the moment, we are following a supervised approach, allowing detection and explanation of known attacks. However, since we ultimately want to detect 0 days as well, we are also working on an unsupervised version. To achieve this, we plan to train the model on graphs that include benign edge, as well as edge that doesn't exist and will serve as counterexamples. This allows to penalize the model and if try to overfit by classifying everything as benign. But as mentioned, it's still ongoing work on our side. Now for the experimentation, we obviously need a dataset. However, there is currently no established dataset in the 5G literature. For anomaly detection, I mean. Only 2 datasets in the literature position themselves as official datasets and make their capture publicly available. However, they mainly consist of user traffic, which is not relevant in our case. Obviously, the anomaly detection paper we presented earlier also have to do a dataset, but each of them typically generate their own and rarely shared it. As a result, we also had to build our own dataset. The version we generated and used is available on Zenodo. You can also access the GitHub repository to reproduce the attacks and see how the benign traffic and the scenarios are implemented. An associated paper describing the dataset content and quality verification of the content has already been written and will be made accessible shortly. But just for a brief summary, our dataset was generated using FreeFiGC and URNSIM. It contained 4 hours mixed of benign and attacks. We include 9 benign procedures and 10 different attacks. As you can see, we try to design attacks that cover multiple dimensions at once, and we also conducted validation tests for each dimension to ensure that we did not introduce biases in our attack generation, and also that the dimension we define correspond to the real ones. For our training, we used DigiLib library, which implements several state-of-the-art models. We observe that the best performing model is TGN, the one we presented earlier. It achieved nearly 95% accuracy and precision, which are still hindered by some labelization issues we identified. There are still quite a few experiments we could run on hyperparameters, so we could still tune the model a bit further, and the result could be a bit improved. As we mentioned, since the current approach is supervised, it mainly detects attacks we have already been seen. However, instead of simply producing binary alerts at the flow level like traditional IDS system, we can precisely identify which parameters are problematic. Here you can see an example of a graph full of benign on the left and another with attacks on the right. The anomaly prediction is represented by the color of the edge between the node, with red being a certain anomaly and orange being an uncertain one. And the green, obviously, are benign. So this solution is highly explainable, and you could see exactly which parameter the model raised its alert based on. So that's the end of my presentation. I have to be short on some specific part, for example, the dataset, which is a paper on itself. So if you have questions on it or want to discuss about it, I'm here the rest of the day, and I will be glad to talk to you, especially if it's in French. So yes, if you have any question, I'm available.
Thank you, Thomas. Thanks. Cédric.
Thank you for the talk. When you say you have 95% of precision, is it due to misclassification of attacks, or it's 5% of false positives?
It have issues both on some benigns and some attacks, but some of the issues we have, for example, if you see on the graph, some packets, some attacks are classified as benign because, in fact, they are the response of the attack. So the problem is the labelization in the dataset, where I did it a while ago, and I have to correct it. But the response was tagged as an attack, and it hindered the detection. So we maybe lost the 5% accuracy on it.
You have no idea of how many real false positives or false negatives you have?
Yeah, I do, but I can show you to you later. I have the confusion matrix with the true positive, false positive. So
okay, thank you.
Thank you very much. Really, really cool work. Just a follow-up on the previous question. So it's 95%, but of what? So is it every event that you're counting? So because does that mean 5% represent potentially thousands and thousands of things to look at, or is it a different granularity?
Sorry, I didn't really quite understand.
So you said 0.95.
Yes.
So there is 5% of error, right?
Yes.
So, but is it every event is potentially an error? And since in a normal 5G network you have millions of events per day, that would be a lot. 5% would be a lot, or is it counted differently?
Okay, the first half of the question is yes, we count every event as an individual error, maybe. But the fact we don't have a million of events in 5G network because we consider the control plane and not the user plane. So we have way less events that go on our system. For example, we have one procedure for when a phone wants to do registration. It maybe create 100 events, but not much more. So we won't have a problem about the quantity of the volume of message.
Less. Yeah, the problem exists, but less.
I guess I have a follow-up question if nobody has a question. Yeah, so following up, how this thing scales up. I mean, could you consider real-time monitoring with your solution?
As I said, there is not much volume of packets, so we are processing 300 per second, which could be enough in a small network, but it's with really bad models because the implementation we used is not optimized at all. They allocate the memory of all the nodes they will see, and it's not designed to do a real time. So if we optimize it, it could be way much better and would be enough for control traffic.
Thank you.
Other question? No. Oh, so
Yes,
thank you. Thanks a lot,
Thank you,
Thomas.
Thomas.